So we'll wait for another few minutes.
So yes, just so that we can get a few more folks attending. I see somebody's attended already, Ramesh. Can you hear us okay? You wanna?
Yes, please. Absolutely. Can you hear me okay?
Yes, mate. Yeah, all good.
Oh, excellent. Thank you. Awesome.
Yeah. Yeah, I reckon we wait a few more minutes and then we'll start. I'm expecting. Oh, here we go. No, that's not. Yeah, we've got some more people attending. Give it 2 more minutes, we may as well start. Since we're recording this session anyway, then we can make sure we share the URL for the session with those people that have registered. So yeah, 2 more minutes. All right, I think we can make a start, Osborne. So I'll just introduce ourselves to everybody that's on the call. So greetings to everybody. Osborne's going to be presenting a couple of sessions. First session today, and the second session we'll do Friday next week. The first half is sort of more about the various types of interfaces and things like that, and then the second one next week is more geared towards giving people a bit more understanding on things like JESD 204, A, B, and C, etc. So any questions, please type them into the chat window, and we'll try and answer as we go along. And if we can't answer it right here and then, we'll come back with the questions and answers and share them with people that have attended. So yeah, over to you, Osborne.
Okay. Good day, everyone. Nice to meet you here. Today we will talk about the ADC interface with AMD FPGAs. I'm Osborne Liu from ExcelPoint, application engineer here and a dedicated AMD FAE for FPGA products. So we chose this topic because during our work, we kind of came across many applications that use both ADCs and FPGAs together. And such applications like software-defined radio, measurement instrument, and motor controllers. All those application requires analog to digital converters, and FPGA usually is the first choice to connect with those ADCs. So we hope this session will help our customers to understand more and to design a good interfacing between FPGA and ADCs. So when we look at the data sheet of ADC and DAC, normally we can find two categories of interface. One is non-gigabit interface. And this kind of interface can also be divided into two subcategories. One is differential interface, one is single-ended interface. Today, we won't talk about SPI single-ended interface. This interface is focused on the low-speed ADC, and it's not our focus. We will talk about other interfaces that focus on the high-speed application. And in next session, we will talk gigabit transceiver interface. And those interface usually has a speed higher than 1 gigabit per lane, and it's covered by GESD 204 protocols. And we said FPGA usually is the first choice to connect ADC. Why we said so? Because FPGA can provide flexibility. It can adapt to many different ADCs and DACs, and all the FPGA code has reusability. You can use same code by changing some parameters, then use it in another design. And that makes development much quicker, and you can push to the market as soon as possible. And also because FPGA contains abundant IOs, that makes one FPGA can host to multiple ADCs that provides a way to do a high density design. And of course, the speed. I don't think there are any devices can compare with FPGA on this I/O speed, because we can up to like 1 gigabit on normal I/Os and 112 gigabit on transceivers. Today's session, we will talk mainly focus on non-gigabit transceiver interface, and the next session we will talk gigabit transceiver interface. So for this non-gigabit transceiver interface, first, if we look at the differential interfaces, the first type is serial differential interface, and one typical voltage standard that is used is LVDS. So this kind of interface usually it contains one synchronous clock and one differential pair of data length, and also a frame signals that marks different ADC and DAC data. And this kind of interface, it can run like up to 1 gigahertz per lane per second, and it's quite good for performance, and also it behaves quite good at noise performance. The second one is parallel differential interface. This interface compared with serial differential interface, this one, it uses multiple pairs of differential data lengths. And also the ADC and DAC data actually is transferred in one single clock cycle. That means this interface can run multiple times faster than the previous one. So it usually used for many high-speed, low-cost ADC, like the example we will show later, the ADI devices that use this parallel differential interface. The third differential interface is DDR differential interface. This one is quite similar with the parallel differential interface, but with the same data throughput, this interface reduces the number of the data lengths by half, or if they use the same numbers of the data length, this kind of interface can provide double data throughput than the parallel differential interface. And for this kind of interface, all ADC and DAC data bit actually it's transferred on the same edge of the clock. And at the following edge, it will transfer another ADC DAC data. So this is three kinds of differential interfaces you can find in ADC datasheet. All those examples are from ADI ADCs, which we also supported by us. So if we continuously, then we will see this parallel single-ended interface. This interface, the purpose is to reduce pin consumption, because differential compared with this single-ended, it uses 2 times more pins of device. So, sorry. So this one, it only uses parallel single-ended signals, and it saves half of the pins, but because it's single-ended signals, for example, CMOS, it's more easily suffered to the noise and suffered to the what we see is a crosstalk. So it usually recommended to use at as a very short traces. Don't put ADC and FPGA too far away to each other, especially when ADC and FPGA need to be placed on 2 different boards. We won't recommend this type of interface. And this interface usually need to be coupled with very small capacitors to reduce, we call it common mode noise. For the last, it's DDR single-ended interface. This interface, it's similar to the parallel single-ended, just transfer 2 bits in 1 clock cycle. So this is just to reduce the pin consumption further than the parallel single-ended interfaces. So this is usually, these are 5 different interfaces you can find in a ADC or DAC datasheet. And all those interfaces, when you design it with it, and you will find there are some common feature you need to deal with. First, you have an application, and you probably do the same processing after you got ADC signals. But the ADC you chose, Some may be 14-bit, some may be 16-bit, and some may use LVDS, parallel LVDS interface. Some use DDR LVDS interface. So that means you have same application, but you need this application to support different interfaces. That makes FPGA very good for dealing such requirement, because FPGA with a generic in which there are parameter in Verilog language, you can simply switch it to a different type of interface. Another common feature is that actually there's always a synchronous clock, and this synchronous clock always run at a certain phase and frequency relationship with data. So when design the interface with ADC, you always need to guarantee that receivers can receive all the data correctly according to the relationship between its clock and its data. So for FPGA, we have many special resources in our I/O blocks, which can help to do this task. And another common feature we can find is usually it's just one direction with high-speed data rate. It's just from ADC to FPGA or from FPGA to DACs. On other way, it's usually just a slow speed SPI to send some control and settings. So this is all the common features that when we design an interface between ADCs and receivers, usually FPGA, this is all what we need to take care of. And so AMD FPGA, we always said we are the best choice to connect with ADC. Why? Because we have special FPGA I/O resources, and these I/O resources can provide great flexibility for you to connect with ADCs. So what FPGA resources we have? First, we look at the FPGA I/O interface types. We have high density I/O, high performance I/O, high range I/O, and the latest XP/IO and X5/IO. For all those I/Os, it supports different voltage range. So if you have a CMOS 3.3 voltage standard, you can choose HDIO or HRIO. All those IOs actually it is supported in different device. Like normally, you will, when you choose 7000 series, you will use HPIO and HRIO. For Ultra Scale Plus, you will have HDIO and HPIO. And the speed they can support is different. For the HPIO, if you use LVDS signals, it can run up to like 1.6 gigabit per second. That's the highest speed, but you need to check all the data sheet to find out the final speed you can support according to the voltage you choose. And also we have a lot of I/O pins. See, the total I/O pins can reach to nearly 2,000 I/Os, and that can support a abundant of peripherals that connect to the FPGAs. So this is FPGA resources for support different voltage and to support multiple peripherals, but also we have resources inside FPGA block. These resources like I delay, O delay which is add extra delay into the I/O pins, into the I/O signal that you want to control. For example, you want to delay clock more than that, then you can add a delay to the clock signal path. Also, we have IDDR and ODDR. This is to convert DDR signals into parallel signals and reduce the speed. So you can process that in a lower clock speed inside FPGA. And we have S30s and O30s, which can support even higher speed than the IDDR and ODDR can solve. This one, yeah, the maximum is 8 times slower than the I/O. So that means when you got a 1 gigabit signal on the I/O pins, actually inside FPGA, you can deal with it under 125 megahertz clock. That makes coding and mapping everything much easier. And we also have the input and output flip-flop. This one, it can capture or clock out data as quick as possible and reduce the delay between the internal logics and the external pins. So for some application, if you want to capture the input data with the minimum delay, this will be very helpful. And we also have some features for signal integrity. For example, the internal differential termination. This is for the differential input from outside, and also we have digital controlled impedance. This is kind of a method for the source termination. And for the new I/O new devices, we also have X5s and Nimbles, which is support even higher speed applications. So when we design an interface to the ADC, we can see if we saw an ADC interface type, for example, we saw a parallel LVDS, then we know according to the voltage level it used, we probably can choose HDIO, HRIO, and HPIO. And according to the, because it's a parallel LVDS, we need to convert it into a single signal inside FPGA. So we will use iBuff DS. And if it's a DDR signal, we can use IDDR. Or if the speed is really high, we can use I30s. And also iDelay, probably we can use it to adjust the phase relationship between data and the clock. For the output side, same resources we can use as well. So, but how to use it, we can do it in this way, for example, okay. When you find an interface that running in the in a SDR mode, which is like a parallel single-ended or parallel differential interface. And for this interface, actually, you can simply use IOFF to capture it or to output it, and use the output constraint or input constraint. After you're doing this, Vivado will guarantee the relationship between the clock and the data. And if necessary, Vivado will insert delay for you. So that means this design is the most simplest interface design, and you can use it very easily. But it only for the signal speed set less than 200 megabit per second, because if you want to run like a 400 megabit per second. That means your FPGA has to run as faster as 400 megabit per second inside, and that will be a difficult for your design. The second method is using IDDR and ODDR. This is typically for the DDR per single-ended and DDR differential interface, and with limit that data speed is less than 600 megabit per second. So by using this IDDR, all the input data will be converted to the parallel data inside, and the speed will be the half of the I/O speed. So 600 megabit per lane will be 300 megabit inside FPGA. And for this kind of application, you can, like the previous one, you just use input and output constraint. And Vivado will add this delay for you by calculating the phase path delay for the clock and the data, and try to add this I delay and to maintain the relationship between the data and the clock. The third way to deal with the interface is the most challenging way to do it. It's using the I30s and the O30s, which means for the data that in high speed, for example, 600 megabit per second in DDR mode or 300 megabit per second in SDR mode, for those kind of incoming data, you need to convert it into multiple parallel bits of the internal signals. So I30 is a must to do this job. And you need to control the delay on data or on the clock. Based on your selection, it can be as simply as just adjust I delay on clock, or as complicated as adjust I delay on data and clock at the same time. But this one requires more sophisticated algorithm to adjust it, or you need to adjust it manually to on each lane by setting registers in your design. So this is usually for the very high speed ADC interface, and this one you cannot do it simply by the constraint. You have to adjust it manually or wrote a special logic module to adjust it automatically. And if you want to just adjust I delay on clock, make sure the length of data and clock is matched on the PCB design. Yeah. So we have an example design here for this kind of application. It's a ADRV 901 board connected to our FPGA board. And in this board, in this design, you can see we have differential input bus to convert differential signal to a single-ended signal inside FPGA, and we have I delay, which is controlled by the setting registers, and we also have I30s, which convert signal from one lane to the 8 parallel lanes. And by this way, the internal side only run at like 125 megahertz, and the interface here can run up to 1 gigahertz per second. So it is difficult to use to some extent, but I would say if you got problem coming to us, because Excel Point we support both ADI and AMD as well. So we got plenty of experience on how to solving all those interfaces. And meanwhile, AMD did a lot to help people to use it. Like AMD provide all those I/O wizards. Like Universal, it is advanced I/O wizard. In UltraScale Plus, it's high-speed select I/O wizard. And in 7 series, it's select I/O interface wizard. All those 3 wizards, for example, Universal, it's advanced I/O wizard. This is designed for the high-speed application that include X5 function. But this one, it doesn't include the IDDR, ODDR, or simply the I/O block registers. But all those features, if you want to use it, please use it in the HDL code. And this is the interface when you try to use this wizard. You will see you can set clock input speed, clock phase, and you even can have the pin assignment before you got the whole design and got the I/O timing estimation. That will save you a lot of work. So you can make sure your I/O timing is satisfied before you finish all your design and do the test and found the problem later. You can solve it earlier here. For the UltraScale Plus, we said there are high-speed select I/O. And for the 7 series, we have select I/O interface wizard. This wizard, it includes I30s, O30s, so you can set it, but the logic to control the I delay or O delay, you need to design this logic or use a manual way to control it by setting a register value for it. So all these wizards you can use in Vivado that helps you to faster your design and save some your workload, but not just the ADI, ADC, and AMD FPGA you need to consider when you design such kind of interface, because what we are talking, all those interfaces are usually used in high-speed ADCs, not low-speed ADCs. So there are some points regarding the external circuits between FPGA and ADCs need to be considered. We will discuss this in 5 different aspects, like trace, termination, coupling, vias, and connectors. The first you need to consider when you design the interface between ADCs and FPGA is the trace. And normally we said trace. We talk about the impedance. And for the single-ended I/O, we always said the trace impedance should be 50 ohm. And for the differential I/O, the impedance should be 100 ohm. But you know, the trace impedance are related to the geometric structure. It's related to the material you used. It's related to the trace-wise thickness, and even the surface roughness also related to the trace. So always there are some trace impedance happen, mismatch happened. And when this happened, some reflection will happen as well. So we can calculate this reflection coefficient by this formula. And all the reflection means some kind of power of the signal is lost. So what we do, we need to match all the impedance as much as possible, like from source to the trace, from trace to the destination loader. And also we need to take care about the connectors and the wires along the trace, because that's the point where the impedance discontinuity could happen. And besides the trace, we also need to take care about the reference plane close to the trace, because every signal that transmitted along the path need a equal and opposite complementary current to flow back to the source. So any interruptions on this reference plane will also cause impedance discontinuity. So always make sure the reference plane is continuous and not isolated or splitted by other signals. Besides all the impedance requirement, there are also some other requirements when you're doing the interface between ADCs and FPGAs. First is always route all those interfaces at the highest priority. Because yeah, I got some bad experience when not doing this. Because by doing this, it will reduce wires and reduce the bands that may happen when you're doing the PCB, and that reduces the potential for impedance discontinuity. And also route inside PCB, not on the top or the bottom of the PCB, because inside the strip lines, it suffered less noise and interference from other signals. And for all those BGA like packages, you need a route from the pin to the internal layer of the strip lines. So remember, keep all those macro lengths as short as possible, and do not bend signals in 90 degrees. Always use a 45-degree bend. For differential signals, not just the length match of different pairs, but also we need to match the length inside one pair. So that makes sure it won't affect differential voltage swing that can be received by the receivers. So trace, we talk, the second we will talk about the termination. Termination is a very important method to keep the source and destination have the same impedance as the trace. So like for single-ended signals, usually we have two ways to do the termination. One is parallel termination. Usually we put the termination resistors next to the destination device. Another way is serial termination. This way we put termination resistors next to the source device. So in FPGA, we have LVDCI and LVCMOS features. For LVDCI, actually, it's kind of source termination. By selecting a proper output termination, you can remove these resistors on PCB. That will make it signal integrity much better. But this function only supported like in the HPIO banks. For HDIO and HRIO, high range IO, you cannot do this way, but because it in most cases you use LVC MOS, so set a proper drive strength like 6 milliamp and use the fast slow, not the and by this way you will have a nearly 50 ohm impedance at the output of the FPGA pins, and that also makes source termination as well. For differential signals, usually we use termination next to the destination device. It's 100 ohm resistors between positive and negative signals of differential pairs. But for this one, in FPGA, we have on-chip input differential termination. Enable this function, FPGA will terminate all the differential signals inside FPGA, and that completely can remove this stub. And also it improves signal integrity. At the meantime, it helps the PCB layout to save a lot of spaces, because if you have like 16 pairs of LVDS signals, you need 16 resistors, and for the BGA package, it's usually difficult to find a proper position to put them. The third aspect when we're talking about the circuit between ADC and FPGA, it's coupling. We recommend AC coupling between the trace and FPGA or destination devices, because especially for the parallel CMOS interface, by using AC coupling, it removed DC current and reduced power consumption. And with this kind of AC coupling, it also removed common mode voltage. But remember, when you use AC coupling, it kind of behaved like a high-pass filter and may introduce inter-symbol interference. This may cause some issues, but for the parallel CMOS, it's okay as long as you keep the trace short and keep the ADC and FPGA close to each other. For the differential signals, normally we saw this AC coupling only on the clock signals, and the smaller capacitors is better. And the advantage of this AC coupling is mainly because we can connect different voltage standards. So when you check the AMD FPGA I/O datasheet, you probably found, okay, in some signals, we didn't mention what type of voltage standard we support. That is because we use AC coupling. So it's okay to use different standard of voltage, as long as all those voltage can satisfy the SWAN requirement. So the fourth aspect we talk is bias. Bias usually is needed when you want a signal to transfer from one PCB layer to another PCB layer. And for a bias, we usually say it has a barrel, and it also has pad used to connect to the trace. And it also has an anti-pad area. And this structure of the bias related to the impedance So make sure talking with your PCB manufacturer and make sure this vias is has the impedance you need. And the vias, there are many different types of vias. For the normally one is through-hole vias, and for the interfaces we talked today, this is okay for all those applications. But in the next session next week, this kind of through-hole vias will not satisfy your signal integrity. So at that application, probably you need to consider buried vias, which is connect to internal layers, or blunt via that connect from top or bottom layer to the internal layer, or use back-drilled vias. This will improve the signal integrity, but also it will increase the cost of PCB manufacturing. So for differential signals, we cannot just make differential signals change layer. We also need ground vias. So it's called ground signal ground type differential vias, GSSG. By this method, it can guarantee when the differential signals change reference plane, the return current will have the closed path next to the differential signals and make sure the signal integrity behaves better. And also there's a kind of a hole here without any PCB, without any ground. This is the whole size also related to this GSSG impedance. So calculate it with PCB manufacturers' tools and make sure have a proper 100 ohm impedance for the differential signals. The last but not least is a connector. It's very popular when we put ADC on one board and FPGA on another board. For example, in our demo, we have ADRV901 on one board, and we have Zinc MP-SOC on another board. So connectors also very important for the signal integrity and also important for the structures. We cannot just simply use any connectors we can buy from the market. So we said to connect ADC to FPGA, now we recommend to use FMC connectors. This connector is recommended for connect parallel or LVDS signals from ADC to FPGA. But if the speed you need to connect goes higher, then you need to contact with the connector manufacturers and find a proper one for your application. Also, for the ADC input side, we said you can choose from all those connectors, and these connectors, they will satisfy the impedance requirement and also satisfy the frequency that you need to keep it pass from the sensor to your ADCs. So this is our today's session, and some main takeaway we can see. FPGA, it's the most popular device to control ADCs and DACs. And to do a proper design for control ADCs, you need to choose the proper I/O resources and always keep in mind match the impedance, working with the PCB and the connector manufacturers, and also utilize all those internal impedance that provided by the FPGA, so that the impedance discontinuity won't affect a lot on your design. And because Excel Point, we can support both ADI, maximum LT, and ADCs, and AMD FPGAs. So if you got any issue, coming to us, and we will be glad to help. Thank you.
Thanks, Osborne. Could you go back to the previous slide? Yeah, so there was a so you talked through about FMC, SMA, SMC, but there's a question about whether you would recommend SMB connectors.
SMB, that depends on your requirement, but this is just example. Not said you cannot use it. We just said this is very popular when you do the design. So SMB, as long as it can satisfy your impedance requirement and your speed requirement, it's okay, no problem.
Cool. So we haven't had many questions come through, just the one. So anybody else got any questions? Either type them or unmute yourself and ask. No? Okay, so what we'll likely do is this session has been recorded, so assuming I can figure out how to and where to find the recording for it once I've got it off the Zoom, we'll make that available to you guys. The next session will be, I think, the same time next Friday. Again, roughly about an hour. It's just a nice opportunity to work through the material. We would welcome some feedback if there's other things that you're interested to see. But yeah, this is sort of geared towards a bit more of an overview, and yeah, hopefully the next session will give you a bit more detail about JSD interfaces.
And
so
the AMD transceivers.
Absolutely, yes, the AMD transceivers. So yeah, if there's no more questions, I'll stop the recording and we'll see you guys next week. Awesome. Oh, hang on. Do we expect okay. Do we expect any hands-on sessions with examples using your choice of any ADC? So today and next week is not so much on the hands-on side, but that's I see the likes of Sean and Isam, then that's something that
if you are
we can talk about.
interested, you can email me and I can find some examples if you need.
Yeah, cool. All right, well, yeah, thanks folks for attending, and yeah, we'll see you guys next week.
Thank you so much.
Thank you. Cheers.